My name is Professor Klumpe. A lot of you do know me, but for those that don't, I'm a professor of astronomy here at MTSU. MTSU's been my home for 17, 18 years now, and they have been some of the most wonderful years of my life. Nothing brings me more sense of purpose than to be in the classroom. That's something that really means a lot to me, probably more than I can express with words. We have to balance a lot of responsibilities as faculty. You know, you have research, you have committee work, you have to serve your professional community, conferences, but there's one thing I can say beyond all doubt that I love more than all those things. It's being in the classroom. And I'm very grateful that MTSU is they so strongly encourage that, let's say, okay? I was offered positions. One position I was offered, I would not have been in the classroom at all. I would have been an astronomer on the island of Hawaii. There was a few positions where I would have had, it was for a national lab, again, not much teaching. Another position I was offered was in Wisconsin. I probably would have been in a hectic publish or perish world. I think it would have sucked the life out of me. I think it would have been my doom. There are a lot of people who are very good at that sort of thing, and I will gladly encourage them to pick up my slack. The physics department here has quite a few people who are actually excellent in research and probably excellent in both teaching and research. So maybe it's good that I'm getting old, I can retire and make room for the next generation. But I'm glad you're here. Friday afternoon, Friday evenings, excuse me. That's a big time. That can be a family time. Okay, I'm going to start over. My name... I'm glad they're here. But you're carving out a very important time slot in your life to be with us, and I appreciate that very, very much. Let's get started. We could adjust the lighting. How do you feel about the lighting? Could it be better? Bright. You like it bright? No. You like it dark? Yeah. Okay. All right. I'm half. Okay. I do not know if these 5 buttons represent a linear scale. Yeah. I am going to hit the next to the brightest button and see if that's a good thing. Better. But not significant. Let's do the third one. That's better. That's better. What about that one? That's better. What about this one? What about this one? Okay. All right. And all right. Well, let's get started. Black hole trivia: A Tale of Two Perspectives. Oops. Well, black holes are, well, I think everybody in this room, to a person, and that includes this gentleman here, and that little girl over there, we all love black holes because we see them on TV. When they describe how they work, they sound almost too weird to be true, and they're really, really fun. And of course, when you develop the mathematical basis to study them like a physicist would study them, they don't lose their glamour. They're very, very fun and very, very exciting. And this is something I'd like to spend time with you today. I also have a nickname. It doesn't come out that often, but I tend to ruin subjects that are fun by describing them more accurately than they would be in popular sources. And it's possible tonight I will reestablish myself as the ruiner of everything about black holes. But everything I'm going to tell you is true, and so you don't have to worry about that part. Okay? Here we go. December 1st. Okay, a little bit of history. This isn't the first time I've spoken on black holes. Generally, what I like to do, and have been doing for a few years now, is we usually talk about a popular film or films that have a common theme related to physics, and we break it down. My intent is that you would generate some appreciation for maybe the lead actor, the lead actress, the director, you know, a lot of artistic vision, and that you get excited. And so we don't try to make fun of people, but we do point out that things probably don't work the way we see them on movies, but we try to do it in a nice, kind way, and we get to enjoy some clips. So I've done some past talks. I don't know, how many of you remember this one, November 1st, 2013? We did Galaxy Quest, and we talked about going through a wormhole. For that reason, I can't spend too much time talking about wormholes tonight because I've already done it. But during Q&A, if you're in the mood, we can readdress wormholes. I don't know if you remember this. November 4th, we did Miller's Planet and Gargantuan from the movie Interstellar, one of my favorite directors. Supermassive black holes are amazing things. And not only that, this supermassive black hole spins physically as fast, according to the way the story is described, as fast as any black hole could conceivably go. We spent some time on that. So a lot of that we will not address tonight. A little bit of background. Let's talk about our background. We need to all be on the same page. Let's begin with probably the most common description. Please, come on in. It didn't feel right until you guys got here. It just didn't. Thank you. Now I can continue with a clear conscience. Okay. Who would like to volunteer a definition for a black hole? And we'll just see when I reveal my bullet points how close you came. In the back.
A point of infinite mass and infinite gravity.
Okay. A point of infinite mass and infinite gravity. All right. Go ahead.
A point of finite mass and finite gravity.
You know, who's been with me long enough to know what is the appropriate way to resolve academic disputes? What was it? We go to the loading dock and we duke it out. Where's the loading dock?
It's not here.
It's the annex now. It's the thing that connects the two. We used to go there and resolve our disputes like men. Okay? And we did that. So this would be a perfect time. We would dismiss just for a few minutes. We'll see who's actually right, and then we'll come back in. Okay. We can talk about that. I appreciate your feedback. What else can we say about black holes? What's another? Go ahead.
Well, it has an event horizon, and once you pass the event horizon, you're sucked in and can't get back out.
Okay, there's an event horizon that surrounds it. We probably need to talk about what that thing is. And you're mentioning that when you cross over, you get sucked in and you can't get out. Okay. Do you think anything can get out?
Hawking's radiation gets out.
Hawking radiation gets out, but does Hawking radiation begin inside or outside the event horizon?
It's at the boundary. No?
On the outside. We'll talk about that. Okay. What else? Anything else? But I think we hit the bigs. Okay. There seems to be, at least in the minds of folks, that at the center of a black hole, or this thing we call a black hole, is a singularity, something that possesses mass but has no size, because as it gets compressed under its own gravity, there's no known force of nature that we're aware of to resist the contraction. And how big is something that contracts forever? How big is it? Well, you would predict that it would be zero, okay? And then somehow surrounding this thing is something we call an event horizon. If you get too close to it, weird things happen, and if you cross it, you're kind of stuck. You're on the inside forever, all right? Well, that's a good starting point. Let's see what I got here. All the mass of the star fits within an infinitesimally small volume called the singularity. Lasers do not point well on this screen, but old school still works. The singularity is right here. According to the theory of black holes, that singularity has zero size. I don't know if I can understand that. I can repeat it. I can read it in a book. I can listen to it when someone explains it to me, but I'm not sure I understand that. And we'll get into some of my hang-ups about singularities in a bit. The distance between here and here is called the Schwarzschild radius. Schwarzschild was a physicist. He calculated for this particular type of black hole how close you could get to the singularity, where you would reach some point where you could no longer escape. We call that surface, which has a radius equal to the Schwarzschild radius as the event horizon. Now, what does that mean? Are you aware? Okay, if we went outside right now and we're on Earth, I'm going to take a baseball. I'm going to throw it straight up into the sky, and this time I'm just going to kind of throw it ever so lightly. What you would notice is the speed of the baseball would be a maximum the minute it leaves my hand. After it leaves my hand, it progressively slows until it gets to an elevation where it stops. At that point, it reverses course and it speeds up as it comes back down. Now, if I were a young man, I would probably catch it. Since I'm an old man, it would probably hit my pinky and roll over and then get stuck under the chair over there. And I'd say, I'm going to get it later. Okay? All right? Okay. How does that scenario change if I throw the ball harder the second time? What's different? Does it still leave my hand when its speed is a maximum? Yeah. Is it a different maximum? It's faster. Does it stop and turn around? That part's the same, but what's different about the point where it stops and turns around? It's higher. It's higher. I could keep throwing it up, and throwing it up. Eventually, I'm going to get to a speed that when I release it, the turnaround point is way, way past Pluto's orbit. It's just so far away. Okay? That's the speed that we would describe as the escape speed. How fast must you travel so that the speed that that you reach the escape speed for the object you're standing on? If you want to send people to the moon, the rocket, or at least the part that has the people, the part that's going to the moon, has to reach the escape speed for Earth. Or it's not going to escape. It's going to eventually slow down, stop, and fall back in again. Okay? When we're dealing with black holes, one of the things you build on is this idea that the fastest an object can move through space is at the speed of light. So what the event horizon represents is the location in the gravitational field created by the singularity. It's the location where the speed you have to travel to break free and escape is the speed of light. Since nothing can travel faster than the speed of light, if you're ever so slightly closer than the event horizon, the gravitational pull is slightly stronger, but it's slightly stronger just enough that the escape speed exceeds the speed of light. And if nothing can escape the speed of light, nothing can escape. So we got this event horizon, okay? How are we doing so far? Does any of that need to be repeated? Good. All right, let's keep going. Schwarzschild radius, in case you want to know, it's roughly 3 kilometers per solar mass, meaning if we could convert the sun into a black hole, its event horizon would have a radius of only 3 kilometers or a diameter of 6 kilometers. Okay? That doesn't sound too big, does it? But it would have all the mass of our sun, which is, compared to the Earth, quite significant. Light cannot escape the pull of gravity if you're at the event horizon or farther. Okay? Light and matter can enter, but it cannot leave. It's like a one-way door. All right? That's the basics. Okay? That's the basics. A common description of a wormhole. We hear about this a lot. There's a mathematical solution. Who was the first person to propose the solution for the equations? Well, maybe you're right. I'm thinking Kip Thorne. Maybe Kip Thorne came up with the traversable black hole. That's what it was. Yeah, I bet you're right. The Einstein-Rosen bridge. Yeah. There's this idea that you can take a black hole and pair it with a white hole. Oh no, now I got to define a white hole. We'll get there. And if you pair them, space can be shaped or warped in such a way that they actually connect and it generates a passageway. It's a one-way passageway. You can only go into the black hole side and you can only pop out the white hole. You can't go both ways, but popular culture says you can do both. You can't, okay? Let's see. the Kip Thorne paper says they're unstable, but after they read Kip Thorne's paper, they sort of forgot that part, and now it's considered to be common, like something an engineer could make if he just worked hard enough. But he said, yeah, mathematically it's possible, but they're very, very unstable. They're not going to last too long. So even but his would be the traversable wormhole. And a traversable wormhole we'll get into if there's time. But here's another drawing. This is an attempt to illustrate how space would be shaped. What is a white hole? It's a hypothetical celestial object that expands outward from a space-time singularity and emits energy in a matter of a time-reversed black hole. You take the equations of motion, or the equations that describe what a black hole is and how it operates. In every place you see the letter T representing time, replace it with minus T, you've now discovered the white hole. That's how hard it is, and that's all there is to it, because we've never discovered one in real life. No one even has an idea how to make one. But they do exist in the minds of mathematicians and in popular culture. Okay? That's where they exist, but they're fun to think about. They're fun to think about. Okay. We talked about time travel. I dedicate a whole star party December 4th, 2015. Who remembers this one? You guys do? Time travel. We kind of ruined that one, didn't I? That was one of my all-star ruination things, wasn't it? Yeah, sorry about that. So we're not going to talk too much about time travel, but Q&A is coming. And we did wormhole trivia there too. Anyway, but we love black holes. And this is where we're going to begin. Now that we have some basic vocabulary and understanding. Why are they fascinating? And this is interesting. This is a very interesting thought here. Ooh, we got a lot of words all at once. One of the reasons is the wormhole time travel element. That's one of the reasons. When you talk to people, they find out you do astrophysics. They want to know about black holes. This usually ends up here. In movies like Contact, Interstellar, Galaxy Quest, we did these in star parties. I talk about this one a lot in my astronomy classes. We see huge plot twists intimately connected with flying through a wormhole. Okay? Black holes permitted people to manipulate time as well as traversable gateways to relationships with technologically advanced non-humans or to a better life away from the brokenness on Earth. Interstellar. There was that blight. Okay? Plan A, Plan B, remember? But Plan A was never real. Plan A was to try to find a safe home, but it was really, we know you're going to die. Just make sure the embryos get there. That was Plan B. And of course, guy freaks out. Galaxy Quest. Here they're just helping out some intergalactic buddies with Contact. What you've got there is an advanced civilization that has been waiting for the right time and the right person to talk to initiate a conversation with Earth. Okay, and all these are elements. I want to talk a little about J.R.R. Tolkien. I think he would have understood this. And this is a short book that I was made aware of. Anyway, we'll get there. Contact, Dr. Arroway, that's the Jodie Foster character. Oh, Matthew McConaughey, he was the pilot in Interstellar. So apparently if there's a black hole in there, he's going to be cast. Okay? She travels through a series of wormholes. She sees some advanced technology on another planet. She sees herself on a beach, but she realizes it's just some alien intelligence that's just putting this in her mind. She sees her deceased father. Anyway, so the alien tells her that the familiar landscape and the form that the one he projected were used to make their first contact easier for her, and that this journey was just humanity's first step to joining other space-faring species, sort of the beginning of communication with non-humans, for example. Interstellar, there he is, Matthew McConaughey. In the mid-21st century, you got crop blights, dust storms, Dr. Jonathan Brand. He explains the facility's goal is to try to assure mankind's survival. So this is in a situation where Earth is struggling, and we need to find a better place. He's been working on Plan A, but the whole point of the movie there is no Plan A. He's the hero because he pulls Plan A out of a hat. He turns Plan A, which never existed, into Plan A out of Plan B. And Plan B was always the plan. Anyway, They started Plan B, which is to launch Endurance spacecraft loaded with 5,000 frozen embryos through a wormhole that appeared near Saturn 48 years ago. So notice this is an attempt. You've got a hero figure, maybe even self-sacrificing to save humanity. Galaxy Quest, a great comedy, the best Star Trek movie ever made, according to J.J. Abrams. Okay. Anyway, during a Comic-Con convention, Nesmith, who is Tim the Toolman Taylor, it's Thermians, and they want his assistance. It's an extraterrestrial race in need of a replacement commander. Everything they've done is based on the documentaries they've been receiving from Earth, not realizing it is a TV show. And the Thermians and Nesmith travel long distance through space via wormhole. Okay, so what's Tolkien got to do with this? What's Tolkien got to do with this? Why are black holes fascinating? Let me change this. Okay, Tolkien wrote an essay called On Fairy Stories. On fairy stories. And what he did was he tried to articulate what is it about fairy stories that we all find exciting and interesting. And this is, he wrote Lord of the Rings, right? And he was an Oxford Don. I think he worked in 2 different colleges at Oxford. He invented the elfin language before he started writing the stories. Very, very thorough. To Tolkien, fairy stories do not necessarily include fairies and could be written for adults. They are stories that took place in fairy, which is an enchanted realm. That's actually a place, and it's described this way. In fairy, there are happy endings. Love is eternal. You never have to lose the one you love, either to death or something else. There's never any parting. Good triumphs over evil. There is sacrificial heroism, right? People can escape certain death and aging. People can even step outside of time. People can communicate with non-humans, okay? And he argued in this essay that the reason those are fascinating is because they tug on what he would describe as a memory trace. You have to understand, he was a very, very committed Catholic. And what he's talking about probably has close ties with Christian theology, okay? Basically, he's talking about the way the world should have been before the Garden of Eden, before the so-called fall. That's what he's alluding to as a Catholic. He believed that fairy stories are alluring not because they're true, but because we have an innate understanding of the way the world should be. We all know that we will someday die. We will lose those we love. Occasionally, evil does triumph. We won't encounter supernatural beings to help us cope with our problems. Heroes can be cracked and fallen, and we are trapped in time. He would say black holes permit, oh no, this is me. So he would say fairy stories kind of take us away from all those things. It's like a respite. It's a way to get away from the realities of life. We find it all alluring. And he says the allure is a memory trace because he would argue that we're all aware of the way the world should be and not so much the way it is. Anyway, black holes, we pick up on a lot on that list. I don't know if you noticed. We pick up a lot on that list. Because it gives sci-fi writers an opportunity to introduce the elements of fairy into our technologically advanced culture. So now we don't have to put on elf ears at the Comic-Con. We just go listen to a talk by Tyson, and we're there. You see that? So very interesting stuff. A relativity primer. We want to avoid confusion. Okay, this is going to address, I don't know why there's so many words popping up at once. That's not supposed to be the way it was meant to be. But anyway, something that was already brought up. My experience in those students, there is one student for sure who took Astronomy 2040 from me, Benjamin, but there's nobody else, right? Probably not. I don't see anybody. Yeah, you took 2040. I don't know if you remember the story, but as I was preparing, I said, I'm going to finally address some of these misconceptions head on, and I made this a part of my 2040 class, of which you were a student. And he did quite well, in case you're worried. He's one of the better ones. They think about black holes from a spatial perspective. That's not wrong, but they talk about it almost strictly from a spatial perspective. Okay, you have to understand, the effects of gravity affect both space and time. One of the things I want to do is talk about the time perspective, and you'll find out things make a lot more sense. Not everything, but some of the things about black holes make a heck of a lot more sense when you talk about it from a time perspective. Talking about the way gravity warps space. Let's see, tends to spend, I'm not really sure what that point means, but I'm sure it's pithy. Let's see. Okay, an important point to remember. Much of what I'm presenting is from the temporal as opposed to the spatial perspective, okay? Particularly as it pertains to predictions made by general relativity. This is important. Relativity isn't so much about what is happening to you, okay? What you experience. Relativity is about what you would observe happening to somebody else. I'm going to give you an example, okay? For example, in bed, it's 6 a.m. You close your eyes for 5 minutes, it's 7:45. You're late for work. At work, it's 1:30. You close your eyes for 5 minutes, it's now 1:31. What's up with that? Anyway, but does this make sense? Okay. One of the questions people always bring up is, what would happen if you could travel at the speed of light? What does it feel like? If you understand relativity, what's wrong with the question? That's one of the things I want to talk about. What's wrong with that question? Is that a question that you can ask in relativity? What would it be like to travel the speed of light? I apologize. Go ahead.
There wouldn't be any time.
Okay, there wouldn't be any time. All right, we could run with that one. Winston, you have a comment? Infinite energy? Okay. These are all very good. I have to beg your forgiveness. Both of you aren't thinking about this clearly, and I'm sorry. I'm sorry. Go ahead. Sorry, you're in the same camp. This is one of the things I'm going to be trying to deal with. Go ahead. Why not?
You're just going fast.
Okay, you're just going fast. Okay, you've made a good point. Now, my point is right now, all of you are traveling at the speed of light. Relative to what? Relative to, how about the most distant galaxy we've ever observed? Relative to that galaxy, how fast are you going right now? How do you feel? You feel fine. You see, when people say, what's it like to travel the speed of light, in relativity, the next question has to be, the speed of light relative to what? You see? And then relativity begins to explain what's happening at the what relative to what you are experiencing, which is to say, if you could see that what through a telescope, what would you see? You see, you personally cannot feel time slowing down. You personally cannot feel your dimension and the direction of travel shortening. Everything's normal to you because in your frame of reference, you're stationary. You always have zero speed in your own frame of reference. Whenever they use a story to try to explain how relativity works, they say, imagine you're a spacecraft with no windows. You notice they ever say things like that? Because they want the only thing for you to sense is what you're feeling, okay? Based on, not by looking, because if you look out a window, you'll see something go flying by, okay? But at this very moment, all of us are traveling at the speed of light relative to a very, oh, by the way, let me show you some pictures here. This picture describes a huge piece of the universe, both the part that we know, because this is the part where light from those objects have had sufficient time to reach our telescopes. Anything farther than that, we have yet to observe because the universe isn't old enough for there to be enough time for the light to reach us. But what's interesting is, relative to those galaxies, how fast are you traveling? Faster than the speed of light. Absolutely. How do you feel? Is your body getting heavy? Is your clock going nuts? Or did it stop? Looks normal to me. It looks normal to me. Okay, so that's a big misconception we tend to have, that somehow going the speed of light is something I can control. Now, I suppose you could. You could accelerate yourself, but at that point, now we're talking about accelerations. And that's a totally different effect, okay? That's the twin paradox, for example. All right, so how do you feel? The same. How does it feel to exceed the speed of light? The same. Okay, so there you go. A fresh perspective. Okay, most of the laws of physics are symmetrical with respect to time. That means it doesn't matter whether time moves forwards or backwards. So here's the way I defined a black hole in Astronomy 2040. This is how I define a black hole. And we built from here. Okay, here's an alternate definition. Here's an object that's going to be in free fall. Here is a very dense lump of matter. This distant particle, which is on the left, will fall under the influence of gravity towards the massive object on the right. The massive object is a black hole if the falling particle reaches the speed of light before it hits the object. Why do I say that? Because if an object can escape the event horizon, it must be traveling at the speed of light. What's that movie look like played backwards? It moves towards the black hole, and the minute it hits the speed of light, it's reached the event horizon. If it hits the object before that happens, it's not a black hole. This is a different perspective. I'm throwing at you a different perspective. The location at which the particle reaches the speed of light is the event horizon. Here we go. At this point, the velocity is a lot slower than light relative to him. Here, it's not being thrust, it's just free fall under the effects of the gravitational influence of that mass. Here the velocity is speeded up a little bit more. Finally, it reaches the speed of light, and it hasn't hit the singularity yet. That's the event horizon. Now, if I play the movie backwards, it acts just like we've always thought about black holes. It's going at the exact speed it needs to escape. But I demonstrated it being captured because of time symmetry. I can do that. I can do that. All right? Now there's the picture that we saw earlier of a black hole. Okay? How long do you think it takes for a distant observer to see this particle reach the speed of light? How long do you think it takes? What I'm saying is this. Imagine you have a really, really awesome telescope, and you're tracking this object. Now we're going to talk about relativity. What do you see this object doing through your telescope as it's going towards the singularity? What do you see it doing? Because you're going to feel normal. You're going to feel the way you do every day. You're going to get up, all right? And you're going to eat what? A breakfast burrito, okay? And then lunch, what do you eat? The leftover burrito or spam and anchovy pizza, right? We know the best foods in the world, all right? Okay? But everything's normal. But when you're looking at this object, what do you notice? It's going faster and faster. It's approaching the speed of light. What do you notice? Just hold that thought. The point I'm going to make is, based on relativity, not a single event horizon in the entire universe has formed yet. Not one. Not one. If you're going to tell me it has, I'm going to say, show me the picture. And you're going to say, we can't do that. We can only show you evidence of things happening outside the event horizon. That's all we can do. Because the amount of time it takes this object to free fall and reach the speed of light is the same amount of time it would take an event horizon to form as the singularity collapsed under its own weight. It's the same amount of time from our perspective. Okay? Because the material that originally existed for the singularity would have been bigger than the event horizon, and as it falls in, when all the matter of that singularity fits within its own event horizon, that's another definition for a black hole. How long would it take for that to happen? How fast does time go for an... I need a picture. How fast does time go for an object that has just reached the event horizon according to relativity? How fast does time go for an object that's on the event horizon, which could be the last particle to cross the event horizon before it formed? How fast does time go? It stops. It stops. So for me, I would see that if let's say this object that was in free fall was actually a very big clock or maybe a very big digital watch, and I'm watching it, I would notice the ticking would slow, slower, and stop. you would never see it cross the event horizon. That is a relativistic fact. You would never see it happen, which would mean you could never see the event horizon form either. Now, does that mean the event horizon hasn't formed? What if you were what if you were inside the event horizon before it became the event horizon, watching all this material fly past you? Yeah, you would experience it. But what if you took a picture of it as it was happening and then radioed that picture back to Earth? Would it ever get to us? No, it would not. You see that? All right. Okay, so my point is, event horizons haven't formed yet. But notice when we read books, it's like they talk about like they've seen them, like they've photographed them. But technically, it hasn't. Time moves so slowly. Okay, trivia point number 1 continued. From our perspective, watching this happen, it would take forever for this experiment to be completed. Now, this is an expression for special relativity. Okay, this is, I don't know if you can read it, but it says a time interval that has elapsed on Earth. This is the time interval that has elapsed on an object moving at the speed of light relative to us. And that's exactly what this particle is doing. It's exactly what it's doing, okay, because it was in free fall. What is the speed as it's crossing the event horizon? It's c. So what is c squared divided by c squared?
1.
What is 1 divided by 1?
1 minus 1.
Oh, 1 minus 1. 1 minus 1. Thank you. It's 0. And we divide by 0, which means a finite interval, like say a second, would take forever from our perspective. It would take forever. Okay, well, let's start the stopwatch now, and I'll stop it when forever gets here, and that's when the object, you see, event horizons haven't happened yet. None of them have. Not one in the entire universe if Einstein is correct. Is that a trivia point you've ever thought of before?
No.
It's interesting.
It's really weird.
It is weird. I major in weird. But not my diet. My diet is normal. You guys eat weird food. Okay? This is the same expression using gravitational fields. Okay? The Schwarzschild radius is 2gm over c squared. So what that means is when r, which is the distance between you and the singularity, equals the Schwarzschild radius, this term becomes a 1. What's 1 minus 1? We're right back where we started. Because of the way I did the experiment, you cross the event horizon at the same time you reach the speed of light. So both equations work exactly the same way.
That's always good.
That is good. But one's meant for accelerating around a gravitational source, and the other one is an inertial reference frame. But here we go. They are observable from someone outside the event horizon because they haven't happened yet. And that's everybody outside the event horizon. There's no place you can go to improve your view. You can't. There's no place you can go. All right? And you can only see the event horizon by crossing it yourself. That's the only way you can see it. Okay? The trivia continues. Because you are in free fall, you don't even feel the effects of gravity. Have you ever heard that when you're in free fall, you feel like you're weightless? That happens even in the vicinity of a black hole. You're in free fall. What you do feel are called tidal forces. The same effect that gravity of the Earth has on the moon, which misshapens the moon to the point it has become despun, or the same effect the moon has had on the Earth that creates tidal bulges, that as the Earth rotates underneath these tidal bulges, our coastlines experience both high and low tides twice a day. Okay? That's the effect. Yes, you would feel that. You do feel tidal forces. Okay? You don't feel the relativistic effects that we've been describing, only the tidal effects. Well, what happens, and if you take astrophysics from me, and I'm talking calculus-based, we do the calculation. How close can your body get to the event horizon of a black hole where the tension in your body exceeds a ton? That's a hard calculation to do unless you had someone show you, but you can do it. The point is, your feet are closer to the black hole than your head, which means your feet are being pulled more strongly than your head. They're both going down, but your feet are going down faster, which means you get longer. And I think it's called Macaronification. No. Linguinification? Oh, spaghettification. I always forget that word. It's spaghettification. I knew the word. I was messing with you guys. And that's what this picture is meant to show. You would eventually get so distorted that you would become like a piece of spaghetti. That would be real. And your spacecraft would have it too. But other than that, you'd have to look out the window to say, hey, I must have just crossed the event horizon. Are singularities physical? Now we're getting into some of my personal issues. I'm sorry, my dirty laundry's out there now. Those students who know me, what is one of my big beefs in life? Pardon me? I do have trouble with infinities, unless you're talking about my bank account. What else? I don't think physical infinities exist. That is a philosophical statement. I'll just admit that to you right now. I think mathematical infinities exist, but I don't think physical ones do. Okay? So, do singularities have infinite mass? Not necessarily, because the sun can become a singularity if under the right conditions. Does it have infinite density? Well, the best theories that we have available to us today say yes. Okay, that it does have infinite density. So I'm holding on that there's a discovery out there that will say otherwise. But I will admit defeat if I find compelling evidence, which I have not seen yet. I'm talking about physical evidence, not mathematical evidence. It indicates that observationally, we don't even know if singularities are real or if infinite densities are real, which means observationally, you'll never see a singularity in your life. Because if the event horizons haven't formed yet,
Telescopes.
oh, is it clear?
It's clear enough. Hopefully.
I'm going to miss you guys. If it's cloudy, come back. Okay. So we really don't know if singularities exist. We really don't know. And what I mean by that is it's the whole cycle of the scientific method. Have you made the observations yet to confirm your prediction? That's all I'm saying. For a lot of us, particularly if we're mathematically inclined, we see the prediction in the equations, we trust the equations, and we think we found something that's real. But sometimes that's not always the case. So anyway, we don't really know yet. What do we know? Well, we only know what we don't know about what's inside the event horizon. We only know what we don't know. We don't know of anything. We do know we don't know of anything that could stop the collapse. And if you don't know of anything that could stop the collapse, and that's actually a true statement, that nothing can, then it will have zero size. I will agree with that. I understand the physics. I just have a thing about physical infinities in a physical universe. I have a real thing about that. Maybe it just goes with being old. I mean, I can't find my keys anymore. I'm driving with my blinker on. I'm doing all those things. So maybe this is a recent phenomenon for me. You know, oh, those cranky old black holes, they don't have. Yeah, anyway. The density, now if you describe the volume of a black hole as the space contained by the event horizon, if that's the surface of a black hole, not the singularity itself, if that's the surface, in our astrophysics course, you'll be required to prove that density of a black hole goes as 1 over mass squared, which is interesting. That means the bigger the mass, this is an inverse square law, gang. Physics people, I mean, Buchanan should be able to do this. If the mass is big, the density must be small. Exactly. It's an inverse relationship. It's one of my teaching tools. You change the pitch of your voice for inverse relationships. Isn't that weird? The densest black holes are the small ones. The densest black holes are the small ones. The big ones are not. And as an exercise, and we're going to do the exercise here, you could take a ball of water roughly the same diameter as our asteroid belt. Here's the sun. This is Earth's orbit. Here's Mars' orbit. So this is a circle from our perspective, but if you think of that as the circumference of a sphere, if you filled that sphere with a substance that has a density of 1 gram per cubic centimeter, the surface would be the event horizon for that mass. You have made a black hole, and it's not a singularity. Well, it could be. But notice, as we've taken this ball of water, the surface would describe the event horizon. And what happens to the water after that doesn't matter. The surface is the event horizon. Whether it reduces to a singularity, whether it stays as water, or if it stops somewhere in between those two extremes. The event horizon will not change, and the effects of gravity outside that event horizon will never change. So the effects that we talk about, relativistically speaking, don't even require that it be a singular point anyway. The mass has to fit inside its own event horizon. That's all that matters. So the theory does not depend on the mass being at a singular point. It does not require it. It's just that's what we think happens. Interesting thought. Our best guess as to what would happen to that water would be that would collapse into a singularity. But what if it didn't? That was my point. If electrons were point masses, were you ever taught that electrons are like little tiny billiard balls? I was. But I was a dumb kid. And I don't think that's changed other than I got old. All right? But if electrons were point masses, what's the electric field at the center?
0.
No. Well, it would approach infinity. I think technically you're right, it would be 0, but you got to do a weird thing with the limits. Okay? Quantum mechanics informs us that electrons are not tiny billiard balls. We can never localize an electron to a point. You see? Perhaps quantum mechanics can save the day with the singularity in the centers of a black hole. Okay? The problem is, when you try to merge relativity with quantum mechanics, what's the problem? You guys know why that we can't really knit those things together? Quantum mechanics uses operators. Relativity uses physical numbers. You can't equate them because an operator operates on something. And so they use a kludge to connect these two equations, these two systems of equations, and the result is kludgy. Okay? That's why it doesn't work yet. But perhaps an alternate state of matter can resist infinite collapse, another state of matter. And what's a state of matter? The ideal gas law is an equation of state. How does it, when you shrink it, how much does it push back? Equations of state tell us those things. Further consequences. Suppose you're falling in and we're looking out at the rest of the universe. Now let's imagine you're the one who's falling in. Now, other than tidal effects, you're probably, the stretching, you probably aren't going to feel too much, okay? But look at what's happening everywhere else in the universe, okay? Now, how long did 1 second, remember, if you're getting ready to cross the event horizon, what does 1 second look like to somebody on Earth? It's the reverse of what we said before. Okay? It's infinite time. Okay? Which means if you were falling in and as you're getting closer and closer to the event horizon, you would see the entire rest of the universe on fast forward. And guess what? The sun would die, galaxies would probably burn out long before you cross the event horizon. Because the minute you cross the event horizon, infinite time has passed outside the event horizon. Ooh, there's an infinity again. I don't like those. Okay? Isn't that interesting? If you actually did this, because people say, what if you could cross the event horizon and stick your hand in? What would happen to your hand? Well, dude, the whole universe just ran out of fuel. It's reached absolute zero, man. Yeah, you're not, and anyway. Looking outward, you would see a universe moving rapidly towards its end. The universe would end by the time you cross the event horizon. Okay, now this is a picture that illustrates in a very clever way how the universe behaves. The singularity of the Big Bang is here. It goes through a period of inflation. Eventually the background radiation cools off. The universe becomes transparent. Then we have stars forming. Then stars form into galaxies, and then they continue to spread apart. And we see the effects of dark energy as the edges of this thing kind of scoops outward. Time is to the right. Space is up and down and in and out. Okay? So this would go, by the time you cross the event horizon, you could extend this lip in time all the way past Woodbury. I was like, what? That's like infinity, right? No, actually, so you understand? That means if you chose to do so, you can only visit one black hole in your lifetime. You cannot go from black hole, you can only see one. Because by the time you get there, all your relatives are dead. You know, and of course you're getting spaghettified, okay? And you go, can I have some sauce with that? Okay. And actually, you can only visit one black hole in the lifetime of the universe. You can only visit one, which means if we sent a probe with a camera, how many could we see? Just the one. So you have to commit. It's just going to be one. You have to have a probe for every black hole. And no matter how you tried to communicate, no one else would ever know.
You can just make it up. You can fake it.
You talk like a theorist, okay? You can just make it up. You fake it. I've been with those guys. I shared offices with those guys. I used to be one of those guys. I was a theorist for a while. I gave that up. I found out that I did not have the personality for it. Gravitational redshift. Whether an outside observer was watching what happened as you crossed the event horizon, which is what this is, or whether you recorded what happened as you fell in and transmitted it, that's what this is, that information will never make it to an outside observer because it would take as much time as it took for the event horizon to form to begin with. That information will never come out. Never. Never. If Einstein is correct. Any light you transmitted away from the black hole at the time you crossed the event horizon would also be infinitely redshifted, meaning as those photons, assuming you're communicating with light or with radio waves, for the photon to move through a gravitational field in a direction that's away from a black hole towards Earth, okay, conservation of energy would dictate that the photon has to lose energy as it gets farther away. Which has lower energy, a blue photon or a red photon? Red has lower energy, so everything gets redshifted. But if the light was emitted ever so close to the event horizon, how much of a redshift would it be? It'd be an infinite redshift, which means there would be no energy left in the photon. The wavelength would approach infinity. The frequency would approach zero as a limit. And so you don't even have a device to record photons of that low of an energy. You can't record it. Okay? So as an added feature, you would be fried by all the light of the rest of the universe hitting you, because guess what? If you can see stars at night, imagine taking 1,000,000 years of light and having it hit you in 1 second. I could be wrong. Let's see. There's 31 million seconds in a year, and 1,000,000 years would be 31 trillion. So the intensity would go up by a factor of 31 trillion. Yeah. That's going to hurt. And all this light would be extremely blue shifted. So if it's coming in, visible light may be approaching ultraviolet and maybe even X-rays. And you're going, ow. And you're being spaghettified, okay? So apparently the spaghetti will be well done. The spaghetti is well done. Okay, in addition to what we have already discussed, quantum mechanics predicts black holes evaporate via Hawking radiation. Thank you, you brought that up for us. All right, Hawking radiation says, okay, happening in this room right now, happening everywhere in space, are virtual pairs of particles that are very complementary of each other. You're looking good today. Well, thank you, same to you. No, that's the wrong word. That's the wrong word. And based on the uncertainty principle, the duration that they exist as separate pairs is related to the Heisenberg uncertainty principle. The bigger the energy, the shorter the amount of time that they can go into existence. Basically, you're violating conservation of energy for a very short amount of time. They reunite. But if this is happening, and we think it does, in the vicinity of the event horizon, it's possible that there's a divorce. One of the virtual pairs goes into here, and the other one goes out. And the impression you're given is that black holes radiate, but in fact, that's an effect that takes place outside the event horizon. Okay? But it's radiation nonetheless. If it's close enough, how much time does it take for that radiation to leave the black hole? Forever, yeah, or almost forever. Okay, but if you're falling in, guess what? The time difference between what's on your wristwatch and what's happening at the event horizon, or just outside, is getting closer and closer and closer. And guess what happens as you get into that firewall, if you will, of energy that's been emitted and taking forever to get out? You get eons of energy hitting you all at once from below. In addition to the energy from outside hitting you from above. Yes. What happens when I put my hand in the event horizon? Okay. All right. The information paradox. This is fun. The black hole, and this is a paradox that's still being debated today. Quantum gravity is being used, and so we don't have a lot of people who are like in agreement whenever a new breakthrough for the information paradox has been revealed. But nonetheless, we can talk about it. The black hole information paradox is a puzzle resulting from the combination of quantum mechanics and general relativity. Okay? Hawking radiation implies that over time, a black hole will eventually evaporate, leaving nothing. Because when a particle goes in and a particle goes out, you've reduced the intensity of the gravitational field because something has left. If that goes long enough, the black hole will evaporate to nothing and it's gone. Okay? This presented a problem for quantum mechanics, which dictates that nothing, including information, can ever be lost. When you have a wave function that describes what a particle is doing, regardless of what happens to that wave function throughout its history, the information content in that wave function is always fixed. Okay? It can't change. But when you do this, you've just reduced it. Okay? If black holes withheld information forever in their singularities, there would be a fundamental flaw with quantum mechanics. Can't have that. One thought was that information could tunnel out just inside the event horizon, but relativity can't handle that, and that's always the problem when you have quantum gravity. It's always the problem. You're merging two things that don't really fit the way we want them to, like a jigsaw. They just don't fit well, and so there's always something like this. I'm suggesting perhaps the resolution of the paradox is that nothing accomplishes the fall to the event horizon of the history of the universe. There is no paradox, because nothing's ever gotten in. In the entire age of the universe, no information has ever entered, from our perspective, through the event horizon. Maybe that's a resolution. Just throwing that out there. I'm just trying to stir things up a bit. Because you guys aren't riled. I'm going to try to get you riled. Okay?
Well, this is an interesting sort of paradox in data processing. You can process information for free, theoretically.
Okay.
To nothing. But if
Does
you want-
Comcast know that?
Yeah,
Okay, anyway.
But if you want to erase memory, that always costs energy.
Interesting.
So if the black hole is eating up information, it's got to be generating energy somewhere. to do
Huh.
it.
I would tend to think of as entropy. Okay?
You can work it back.
The reason I'm thinking that is you can generate, there is an equation that describes the amount of entropy associated with information.
Right.
Okay? The more ordered the information, the lower the entropy, the more disordered the information. Is that what you're hinting at, or
Kind of.
did I just steal your idea and make it
No,
terrible?
No, it just kind of fits into this in a
Yeah.
strange, weird way.
There goes his thesis.
Well, I'll tell you, because of, if you guys take thermo from me, we get into this. To me, information and the order of the material universe have so much in common, because the way matter is oriented generates information. Can information come out of nothingness? Can you produce an information-rich system when you start out with nothing? Is that possible? And thermodynamics has a lot to say about that. And there is an equivalent law, second law of thermodynamics that you can apply to information theory. There's a very similar law. It's fun stuff, dude.
If nothing ever gets in, then how does the black hole gain more mass?
You're going to have to give me an example of a black hole that gained mass.
If two of them merge?
Oh, okay. What have we seen? What data have been recorded from that event?
That it gets bigger.
Gravity waves. And where do those gravity waves start? Outside the event horizons. This is something that was created, if I may, I did a talk in the Honors College about merging gravity, black holes. If a black hole sitting by itself in space can produce that weird funnel shape, which is the two-dimensional representation of three-dimensional space, you take two of those and you get them to go around each other, you're creating gravity waves. Any two objects that have mass that orbit are producing gravity waves, whether the black holes or not. That's all there is to it. The signature that was detected was associated, the frequency and the intensity, because remember, they got follow-up observations, they know where it took place. It leads us to conclude that it fits our description of black holes. But all we saw were gravity waves. My hand is making gravity waves right now. They're not very big. Okay? So we're detecting gravity waves. This is another example of seeing something that existed outside the event horizons where the time dilation between us and that event is not infinite. That's why we're seeing it. Okay? Yeah. Trivia point number 2. We're half done. Or are we all done? Are we done? This is bad, right? We're not having fun anymore. Oh, okay. Well, anyway. Singularity is a point in time. It is not a point in space. It is a point in time. Imagine you're moving towards a black hole. That's you. Earth, or whatever, is a location behind you. There's Earth. The event horizon of the black hole is a location in space in front of you. So when you're outside the event horizon, you're moving away spatially from Earth, and you're moving spatially towards the event horizon. Once you cross the event horizon, the singularity now becomes a point in future time. Okay? That is what it is. That is what it is. So why are you being sucked into, to use someone else's vernacular, into the singularity? It's because, well, I'll give you my examples here. The event horizon immediately switches. Oh, and by the way, the event horizon becomes a point in your past. Why do you suppose you can't leave from inside the event horizon? To do that, you would have to go backwards. Say it. Words in time. There you go. We got it. We got it. We had to pull teeth, but we got it. Okay. See, that's why you can't leave. You know, you're thinking spatially if you talk about, well, it has to fight this intense gravity, its escape velocity, which is fine.
They don't make DeLoreans anymore.
No, they don't. And that was in my other talk. But because the speed of light is invariant for all reference frames, one of the consequences of the spatial description is the temporal description. They go together, hand in hand. Effectively, the event horizon is now in time past, and the singularity is in time future. Okay?
But I thought you said time stopped.
It doesn't stop for the person crossing the event horizon. It stops when we're on Earth looking at it. It looks like time has stopped. We never see the person cross the event horizon. But if you were that person, you would cross. As you're crossing, you would notice that Earth exploded and blew up, and the cockroaches would still be there. But yeah, and what? Oh, Keith Richards would still be here. Thank you for that. We have sort of like sort of a cultural thing going on here. I like that. Okay. Trying to see the singularity once you have crossed the event horizon is like trying to see Saturday morning at 8:35. I want to see Saturday morning at 8:35. That's almost like a non sequitur, right? That's what it means when you say to somebody, when I cross the event horizon, can I see the singularity? All right? Can you avoid the singularity? Well, avoiding is impossible because it's like trying to avoid the tax submission deadline. It's in the future. You can't avoid it. You can't stop time, okay? For yourself, okay? Your time always goes at normal speed. I like this cartoon because that's death, and he's talking to an IRS agent. He goes, I suppose this was inevitable. What does that mean? There's two things for sure, death and taxes. Yeah. What? Go ahead.
If one day we find a way to control time, does that mean you could escape from it?
I wish I was doing a talk. We can't control time. You can only create an effect where time over there.
I said eventually.
Oh, so we're trusting in things. So yeah, this is called the argument toward ignorance. The future has these secrets. I'm sorry. You might be right, and I will buy you a beer if you are. How old are you? Okay, I'll buy you a soda pop. How old are you?
I'm 19.
Okay, we're going to wait a little bit. I don't think that's possible, in all honesty. Returning to the event horizon is also impossible. It's like traveling to your birth date. I want to go see my birth. That's what the statement is. Could you go back to the event horizon? That's like saying, could you go backwards in time? And the answer is no, you cannot. No, you cannot. Okay? Free fall from the event horizon to the singularity would be 47 microseconds. If our sun were converted to a black hole, it would take you 47 microseconds into the future to hit the singularity. The supermassive black hole at the center of our Milky Way, it would take over a minute. And for a 17 billion solar mass black hole, the biggest we think exists, it would take 3 days. But there's some interesting information. You're stuck on a time axis, and you can't get off it. It's in the future. Okay? If you struggle, which is the same thing as saying creating an accelerated reference frame, guess what happens? You've just shortened the time. You've shortened the time. Okay? Similar for a white hole is time-reversed black hole. So when you're inside, imagine you're moving away from a white hole singularity. Guess what? If you're in a white hole, the singularity isn't in your future, it's in your past. That's why you can't go back. And guess what the event horizon is? It's not in your past, it's in your, I guarantee you will cross. If you put something inside the event horizon of a white hole, it has to leave. It has to. And how fast is it going when it crosses? Speed of light. Exactly. I love this. You guys are getting it. And as you cross the event, okay, we got that. Very good. Once you cross the event horizon, it immediately switches to a location that's behind you. Now, once you cross, it becomes a spatial location behind you. And Earth is a spatial location in front of you. Glad you're here. Unfortunately, you're not going to do very well in the exams because you missed. Oh, this isn't a class. I'm sorry. Yeah, I always give that speech to late students. I'm sorry. You're not a student. I apologize. You're going to do fine. You're going to do fine. All right. Anyway. And white holes are just as dangerous as black holes. Anything it's... Are we done? Oh. All right. For your benefit, the end. Thank you for coming. Okay. Enjoy the concert. Thank you for coming. It meant everything to me to see you guys.
Is it clear out?
Can one of you let us know if it's clear? Can you see the moon? Can you see anything? Just look outside real quick and tell me what you see. All right, you're just going to wave. My voice does not carry as far as I hoped. Anyway, let's get through this. By the way, there is no mathematical distinction, if you actually look at the equations, between what we observe happening inside the Big Bang expansion and what you would see inside the event horizon of a wormhole, of a white hole. They're identical. They're exact same equations. Oh, the Big Bang singularity. It's a point in time. It's not a point in space. You can't fly there. You can't find the center of the universe. But if you can go back in time, you'll find it. Aha. You see this? A lot of similarities. Is our universe really the interior of a white hole event horizon, which is in turn inside a much larger? I don't know. Relativity can't tell us. Relativity, the equations are the same. You don't know. They're the same. So why are black holes black? Black holes are black because nothing can exit. Why can't they exit? Because for light to leave it, okay, you'd have to obtain information from the future. You can't see the future. Therefore, they're black. That's the temporal equivalent of saying that the gravity is so strong nothing can escape. You're saying you have to get it from the future. Okay? And white holes are the opposite. White holes are white because they can absorb nothing. Nothing can enter them. The event horizon is in the infinite past. Therefore, you cannot go into an event horizon because it would require that you go backwards in time, something you can't do. You see that? And this is reminiscent of sending a spacecraft to the location of the Big Bang. Where did the Big Bang take place? Okay, and do we live inside event horizon? Oh, here's a fun problem, and maybe we should bring this in for landing. How large is the event horizon of a hypothetical black hole? Let's take all the matter in the universe and make a singularity out of it. Let's just do that right now. How big would the event horizon of a black hole made up of all the matter in the entire universe, how big would it be? Any guesses? 0. I like it. That's a terrible guess. But that was a terrible guess. All right. It's the same size as our particle horizon. The size of the known universe is exactly the same size as the event horizon if you took all the matter in the known universe and made a singularity. They're exactly the same. The equations are very similar, and they make similar statements, okay? If we lived inside the event horizon of a black hole, the singularity is as unavoidable as it would be in our future, because it would be in our future. In a big crunch universe where space is contracting, some people used to think that when we had the Big Bang, the universe got really big, it reached some maximum size and fell in on itself. If we lived in a big crunch, if we had a big crunch in our future, the big crunch singularity would be a point in time. It would be in our future. Okay? But we're not going to go to that future because of dark energy. But our universe is expanding, so the Big Bang singularity is a point of time in our past. That's what it is. If you want to visit it, you can't fly there through space. You have to go through time. Let's see. I think this is kind of, we've done all this. You can never describe our universe as being inside of a black hole. You can't do that. Let's see. What are we doing here? Oh, it's the end. Okay, good. All right. So maybe that's not support. But this makes me laugh. I used that cartoon before. You pull the plug and you see the embedding diagram of a black hole right there in front of you. It's like, oh no, where is this going? Thank you very much for coming, and I hope you had a good time, because I did. Yeah, I don't know if there's any really quick questions.
Yeah, you described something going in get to the speed of light.
Yeah.
And you're looking at it at your telescope. But the problem is, it's going away from you. So you can't see it because it's not a radiated body. How do you detect?
Okay. You're getting into a very practical, you're speaking like an engineer.
Yes.
We're going to put LEDs on this thing. Yeah. Because they save energy. I used to use incandescents, but I've stopped. Okay. Yeah.
So if you had a black hole up there in the corner, and I flashed a light at it, you're saying the light would never get to it?
Okay. Very good question. If there were a black hole there, the light would, it would take forever for the light to cross the event horizon from your perspective. From your perspective. Yes. But if you went with the light, it would happen as fast as you're thinking. Okay? But as you got closer to it, you would get spaghettified. You would see all the light from the universe coming in on you. The trapped Hawking radiation would be coming out at you. And the minute you crossed and you said, I'm going to take a picture of the singularity, which you can't do because it's in your future, and then you would send it to me, and it would take forever for that photograph to get radioed back to me. So,
That sunburn doing it.
yes. Yeah. Anything else? Go ahead.
Wouldn't it also take forever for you to get out of that black hole?
Yes, because everything is time reversal. Yes. Yeah. It would. Yes. When you emerge, well, not for yourself. You yourself, remember, you don't feel those are relativistic effects. Everything is always normal for you. So you would find yourself coming out. But as you're coming out, you would see a very fast-moving universe. And as you got farther away, the universe would slow down. And when you got to where we call space-time is flat, which is the part of the embedding diagram where it's flat, now time is perfectly normal with you as everybody else who's in flat space. It's all the same. So your watch would match what's happening on Earth. Okay? But just as you came out of the event horizon, at that point, you'd be traveling at the speed of light, and all those time effects, exactly. Yeah, you're exactly correct. Just take the black hole story and reverse it in time, and you've got a perfect description of a white hole that fits with the theory. All right, anything else? Well, I had fun. Now, you have homework, okay? You guys want this? All right. You have to have fun. During Christmas break, you have to spend time with your loved ones and have an awesome Christmas, okay? And thank you for coming.